Good evening, and we resume our studies of the Fourier transform, and we are now doing some inverse Fourier transform. Those of you who are following me can see some problems I did in Washington, D.C. Fourier transform and the inverse Fourier transform. Also, done some problems down here in Sunburn, Los Angeles, California. And we're resuming this evening with our Fourier transform, inverse Fourier transform. So, as usual, my name is Dolphy Gilpin, and let's start off here. And what we're actually doing here is we're applying now the Fourier transform and inverse Fourier transform to circuit analysis, to actually electronics analysis of circuits. And so suppose now we have a circuit, say, this is just 2 ohms. This is given as 1 farad, and V out, and this is the input. And instead you find now V out in the circuit, given that Vi now, we are given that input voltage is equal now to 2e to the minus 3t unit step. So here we're going to apply now our Fourier transform and inverse Fourier transform to solve a circuit, a typical circuit. Well, here and again, now, Ohm's law apply. So what we'll have here is that Ohm's law apply, and we could say now that first, let us say for the V VIF omega is equal now to 2 over 3 plus j omega. This is simply putting this in the frequency domain, the 2 and the 3 and j omega. Well, usually we substitute S for j omega to make the problem more simpler. S equals j omega. And then we convert back to S or j omega at the finish of the problem. So here we have now, we transform now this input time domain into frequency domain. And so we get now from time to that 2 over 3 plus j omega. And now the transfer function obtained by voltage division, transfer function obtained by voltage division is V0 of omega over Vi omega is equal now to 1 over omega over 2 plus 1 over omega, or j omega. And all we do, we move from V0 of that we have equal to 2 plus 1 over j omega. All right, we know that we get now R goes to R. One over j omega c, and inductance goes to 1 over j omega L, or rather j omega L. So the V0 here, we have 1 farad here. So V0 is equal now, the capacitance will be 1 over j omega c, but c is equal to 1, so it's 1 over j omega. 1 over j omega c, c is equal to 1. All right? And resistance remain the same, R is to R, and inductance is j omega L. But we don't have no inductance in this circuit. So V0 over VI now is equal to 1. VI from this circuit is equal to this, the 2, right, by Ohm's law, plus 1 over j omega c, but c is equal to 1, so it's 1 over j omega. 1 over j omega. But it is given now that Vi is equal to 2e to the minus 3t, unit step. Hence, what we have is that now V0 of omega, V out of omega is equal now to 1 over 3 plus j omega 0.5 plus j omega. Or let's don't leave out the steps. We'll get first 2, which is the 2 over 3 plus j omega 0.5 plus j omega. Well, this is the 2 plus 3 over j omega, and 1 over 0.5 plus j omega. V0 is equal to Vi times h of omega, which is equal to 0.5 plus 1 over j omega. Now, by partial fraction, this thing would work out to be now V0 of omega is equal to minus 0.2 over 3 plus j omega plus now 0.4 over 0.5 plus j omega. All right, we do the partial fractions. You have done it. You need to get know that A is equal to minus 0.4 and B is equal to 0.4, something like that. You know how we're going to put that this is equivalent to A over 3 plus j omega plus b over 0.5 plus j omega. And then we do the partial fraction thing and we get a is equal to that, so we return it like that. And so in the end now we could rewrite this now as V0 of omega now equal to in the time domain is equal now to 0.4 e to the minus 0.5 t plus e to the minus 3t. So we go from these steps back into the time domain, and we get 0.4 as the coefficient, e to the minus 3 for this one, and e to the minus 0.5 for this one. You have to know how to handle the signs, you know, because we got that A was equal to, one was negative and one was positive. But always, this is a coefficient of the time, of the coefficient of the exponential in the time domain, e to the minus 0, and this is the index itself, 3, and usually a minus and minus. So that is solving this circuit by using inverse Fourier transform. And the trick about it is that R remain the same, capacitance is 1 over j omega c, but c was equal to 1, so it's 1 over j omega. Inductance, if we had it, would have been equal to j omega L. There was none in this circuit, and it was given that Vi is equal to 2e minus 3t u of t, and we get the frequency domain 2 over 3 plus j omega. The transfer function V0 over Vi by voltage division equals to that we worked out, and we get that. So there goes one problem solved by applying Fourier transform to circuits.